Hello, everyone. So today is our last lesson in Unit 7. Even though I can't physically hear you right now, I am sure you are all rejoicing right now because that means after this lesson and a few more days of practice, you are finished with chemistry. Yay! Okay, so some things you need in front of you right now. You need page 12 of the packet, which is what I have in front of me right now. These are our ideal gas law notes that we're going to be filling out together. You're going to need a periodic table, and you're also going to need your calculator a lot today. So to start out this section of notes, I want to remind you of a lesson we had back in Unit 2 when we were learning about gas laws. You might remember learning the relationship between temperature, pressure, and volume. We learned about Boyle's law and Charles's law and Gay-Lussac's law and the combined gas law. And there was one more law that I left out, and that's the one we're talking about today. I left ideal gas law out because this law talks about moles, or the amount of gas present. And at that time, you did not know what moles were, so I saved it until this unit. So we're back to pressure, volume, temperature. Those are all aspects you probably remember from Unit 2, hopefully. But we're also going to add in moles for this equation. So the ideal gas law, this is your equation, PV equals nRT. And a lot of times this is referred to as PIV-NERT. So if you hear me say that, just know that I'm referencing this law. And the way that you will know to use this law is that the question will mention moles or mass. Now, for this unit, anytime you see the problem talk about gases and volume and pressure and temperature, you know you're going to be using ideal gas law. This little caveat here is just in case you were taking an exam and all the gas laws could be used, this would be how you would know to use this particular law, is that the question will mention moles or mass. So some things to look at here. You've got P. P stands for pressure. And for the ideal gas law, pressure needs to be in atmospheres. So for that, you'll want to remember our pressure conversions. 1 atmosphere is equal to 760 millimeters of mercury, which is also the same thing as torr, which is equal to 101.3 kilopascals. So we'll talk about how to convert later. We learned this back in Unit 2, but again, you might have forgotten that. But this is your reference table for how all the different units of pressure are related. All right, so the next variable we come to is V for volume. Volume for this equation needs to be in liters. So don't forget King Henry died by drinking chocolate milk. If your volume is given to you in milliliters, then you're going to want to move your decimal back 3 places so that it's in liters, our base unit. Or if your volume is given to you in kiloliters, you're going to want to move your decimal to the right 3 places to convert. All right, moving on to the other side of the equal sign, we have N. N equals moles. And of course, that needs to be in moles. And then you come to R. Now, R, I'm going to just point it out up here what R is. R is called the ideal gas law constant, and it is equal to 0.0821 liter atmosphere over mole Kelvin. Now, you don't really need to worry about this. This is just the unit that R is in. But because R is to these particular units, that's why our pressure has to be in atmospheres, our volume has to be in liters, moles have to be in moles, and then our next variable, temperature, has to be in Kelvin. And remember, the way you convert temperature into Kelvin, if it's in Celsius, is just to add 273 to that. So again, this is the ideal gas law constant. Now, another thing I want to remind you of is STP. STP is standard temperature and pressure. Remember, that's just the conditions that are best to study gases. Standard temperature is 273 Kelvin. And standard pressure is 1 atmosphere. So if, like you'll see our next example we're going to do, it tells you that the conditions are STP. So we'll be using these. All right, so let's jump right in and go ahead and do a problem together. It says a sample of gas occupies 300 milliliters at STP. How many moles are in the sample? So I'm going to list out all of my variables. My pressure is standard pressure, which is 1 atmosphere. My volume is 300 milliliters, but remember that needs to be in liters. So milli to the base unit, 1, 2, 3 to the left. So this is 0.3 liters. And then our moles, we don't know, because that's what we're solving for. R is always 0.0821. And then our temperature is standard temperature, which is 273 Kelvin. All right, so we're ready to plug all of this in. 1 times 0.3 equals N times 0.0821 times 273. Now remember how to do algebra. We want to get N by itself, so we need to divide both sides by 0.0821 and by 273. So these cancel, and now we're going to plug this in. 1 times 0.3 divided by 273 divided by 0.0821 gives me, sorry you can't see that, 0.013 moles. All right, moving on to our next problem. It says, how many grams of nitrogen are in a flask with a volume of 250 liters at a pressure of 3 atmospheres and a temperature of 354 Kelvin? So once again, let's list out all our variables. For pressure, we have 3 atmospheres. It's already in atmospheres, so I can leave it alone. For volume, I have 250 liters. It's already in liters, so I'm good there. Now, there's been no mention of moles, but there is a mention of grams. So I'm going to put a question mark next to moles. We'll solve for that, and then we'll convert it into grams. And then for R, that's 0.0821, and then temperature is 354 Kelvin. So that's nice. All of our variables are to the correct units so far. So we'll plug everything in. 3 times 250 equals N times 0.0821 times 354. Now, just like we did in the previous example, you're going to want to divide both sides by 0.0821 and by 354. And the reason we're doing that is we want to get N by itself. So these cancel. So now we're ready to solve. 3 times 250 divided by 0.0821 divided by 354. and I get 25.8. Now that's moles. I need my answer to be in grams. So do you remember how you go from moles to grams? You need to multiply by the molar mass. So let's look at the molar mass of nitrogen. If you look at your periodic table, nitrogen's mass is 14, but there are 2 nitrogens, so 2 times 14 is 28 grams per mole. 25.8 times 28 gives me 722.6 grams of nitrogen gas. And we are done with problem number 2. All right, problem number 3. Calculate the pressure of 5 moles. I'm going to go ahead. I know all of these problems are ideal gas law, so I'm just going to start filling in it as I read through the problem. So 5 moles goes here. 27 degrees Celsius. We don't want that to be in Celsius. We want it to be in Kelvin. So we're going to add 273 to that. And you get 300 Kelvin. And then for our volume, we have 97.2 liters. And then R is 0.0821. So we are solving for the pressure. PV equals nRT. We don't know P. 97.2 for volume. 5 for moles. 0.0821 for R. And then 300 for temperature. So now to get P by itself, we need to divide both sides by 97.2. So those cancel, and let's plug this in. 5 times 0.0821 times 300 divided by 97.2 gives me 1.27 atmospheres. And I'm done. All right, moving on to our next problem. We're on the back now. And I would encourage you, just as practice, maybe to try the rest of these on your own. But if you're not feeling very confident, I'm going to be right here with you solving these step by step. So you're welcome to just continue the video. Or if you want to practice on your own, you can always pause it, attempt them, and then come back and watch the rest. All right, so PV nRT says calculate the temperature. So I don't know the temperature of 20 moles of a gas at 450 millimeters of mercury. Okay, that's our pressure, except we don't want it to be in millimeters of mercury. We want it to be in atmospheres. So if you look back on the front of your note sheet, you'll see that 760 millimeters of mercury is equal to 1 atmosphere. So using dimensional analysis, I'm going to move millimeters of mercury to the bottom, put atmospheres on top, and that's 1 over 760. So I'm just dividing 450 by 760. And I get 0.59. Okay, and then for my volume, I have 5.75 liters, and then R 0.0821. So now we can solve. PV equals nRT. We got 0.59 times 5.75 equals 20 times 0.0821 times T. I want to get T by itself, so I'm going to divide both sides by 20 and by 0.0821. So those cancel, and I can plug this in. 0.59 times 5.75 divided by 20 divided by 0.0821. I get 2.07 Kelvin. All right, on to the next problem. PVNRT. On a hot day, an amusement park balloon is filled with 17.72 grams of helium. Okay, stop there. That's the information they're giving you to find moles. So next to N, we're going to write 17.72 grams. And remember, we need to convert that into moles. How do you do that? Grams to moles, you divide by the molar mass. So we need to look at helium. Helium's molar mass is 4. So 17.72 divided by 4 gives me 4.43 moles. Alrighty, on to the rest of the problem. The temperature is 37 degrees Celsius. So remember that we need to add 273. So we get 310 Kelvin. And then moving on, the pressure is 2.5 atmospheres. And now we're supposed to calculate the volume. All right. So 2.5 times V equals 4.43 moles, 0.0821 times 310. We're going to divide everything by 2.5 so that we get V by itself. 4.43 times 0.0821 times 310 divided by 2.5. We get 45.1 liters. On to the next problem. How many moles of SO2 gas are in 5 liters? There's your volume. A 5-liter container at 21 degrees Celsius. So convert that into Kelvin. 754 millimeters of mercury. And remember, just like we did up top, we need to convert that into atmospheres by dividing by 760. So 754 divided by 760 gives me 0.992. And we're solving for moles, and then we know our constant. So 0.992 times 5 equals N times 0.0821 times 294. Divide both sides by 0.0821 and by 294. So these cancel. Let's see what you get for N. We get 0.21 moles. All right, last problem. You're saying hallelujah. All right, how many moles of ammonia, so we don't know moles, will be needed to fill a 2,000 milliliter container? Now we need to convert that into liters. Moving our decimal to the left 3 places gives us 2. Stored at 10 degrees Celsius. which we immediately add 273 and get 283 Kelvin, and 105 kPa. Now, this is the first kPa problem we've had. If you look back to the front of your note sheet, you'll notice that kPa is 101.3. That's how much is equal to 1 atmosphere. So just like we did with millimeters of mercury, we're still dividing. We're just dividing by a different number this time. We're dividing by 101.3. 105 divided by 101.3 gives me 1.04 atmospheres. And then 0.0821 for our ideal gas law constant. So for pressure, we've got 1.04 times 2 for our volume equals N times 0.0821 times 283 Kelvin. Divide both sides by 0.0821 and by 283. So this cancels, and let's solve for N. We get 0.0895 moles. Okay, well, that was a lot. Hopefully you have seen enough examples now. So I believe that's all you have to do today. Tomorrow you will be doing an ideal gas law worksheet, so you'll be doing a little bit more practice on your own. And then you've got the study guide, and then you are done. You have summer break ahead of you. So good luck. Let me know if you need any help, and I will be here.